And also you can write on it when needed.
Is recording then?
Yeah, there is pause button. Yes. I hope it is recording. Yeah, this
Yeah.
is.
Okay. Yes. Am I audible at the back? Okay. Okay. Hello everyone. So welcome. This is 6.4, the first lecture. I hope you guys are doing well and getting settled, right? Okay. Okay, so this is the course about solid state devices. Okay, I mean, I don't need to say why electronic devices are so important because it has become integral part of our life. Okay, so in all electronic devices or in all electronic instruments or systems, there is a common thing, okay, which is a motherboard, right? There we have billions of solid state semiconductor devices which are interconnected, okay, and forming circuits, okay. So we have two important things here. First, electronic devices, and then with these devices there are circuits, okay. There are two aspects, okay. Yeah, so in this course we'll particularly focus on this devices part, okay. Essentially we like to know how devices operate, the working principle, okay. And there are other courses where you will learn how devices are processed and how you can make circuits, okay. There are other courses. So mostly in most of electronic devices, you will find that it is based on silicon, okay, silicon semiconductor. So this is solid state devices, and at the same time, this is solid state semiconductor devices, okay. That is the focus of this class. So now, so this is one example like of chip on chip devices, and if you really zoom, so here in this wafer, there are billions of transistors, okay. So the size of each transistor is around like 10 nanometers or so. This is very tiny, okay, very small. So this is the kind of devices we'll be studying in this course, okay, including different type of diodes, MOSFETs, okay, transistors, okay, optoelectronic devices, capacitors, among many others, okay. There's a uh, focus, okay, or roadmap of this course, okay. Yeah, so this is the aim. So essentially when I'm saying we need to know the fundamentals or working principle of devices, what do you mean? So essentially we need to learn the IV because you guys are electrical engineers, right? If we apply voltage, so what is the current, okay, okay, and the parameters that determines it, okay, and also CV. Yeah. So for that, if you want to find I, okay, or whatever capacitance or current, so what are the things you need to know? You need to know carriers, right? The carriers which are, okay, moving, right? You need to know carriers, so you need to know the numbers, types, okay, types of carriers, numbers, so carrier statistics, okay, numbers, this come into picture. Okay, now you need to think. So this device dimension, look at the dimension. It is in nanoscale, right? So when dimension is so much reduced, essentially we observe different types of quantum mechanical phenomena, such as tunneling, among others. That's why the quantum mechanics, elementary quantum mechanics is important. Okay, we'll not delve into that in detail. Okay, but whatever things needed for the for this course, we'll discuss. Okay, and finally, so this is, I mean, bottom to top approach. So this is the top end. Okay, so essentially we want to know the device working principle. So essentially, meaning IV or CV. Okay, then carrier stat, quantum mechanics, and finally, or at the bottom, what we have, materials. Okay, for example, the types of materials, silicon, germanium, okay, typically semiconductor materials. Okay, we need to understand material. Again, we'll not spend enough time on that, but we'll spend, good amount of time in understanding the materials, crystal structures. Okay, yeah. So this is overall the roadmap or broad picture. So that means you have material, okay, say silicon, germanium, whatever. Okay, so you need to understand how these materials are grown. Okay, so this is the growth aspect. And when materials are grown, then yeah, so when you have the materials grown, then what you want to fabricate devices. So device fabrication is another aspect. So there are courses, for example, EE618, okay, and among others, where this aspect is taught, okay, extensively. The growth and characterization and device fabrication or related things, okay. So now you know how to grow materials, how to fabricate devices. Then you need to do measurement. You need to understand, okay, the working principle. You need to characterize. So whenever these kind of things come in, like understanding the device, its behavior, this is the course 614. Okay. And now, so you have the device, so basic things are going fine, and now you need to uh, use it for commercial application. So you need to package something, right? So there are other courses for packaging and testing. Okay, and finally, so you have this device, you characterize it, then you model, okay, model the device, you do further simulations. Okay, there are advanced courses, for example, EE616 among many others. Okay, so this is a broad overview of this course, and of course, so this is the device aspect. And when you have devices, so essentially, okay, if I summarize, so growth and fabrication, one of the aspects. Then you have the devices ready. You need to know its working principle. There is a course. Then packaging, testing, and advanced simulation. All device based. And now you have the devices. And with the devices, you want to make circuits. Okay, there are different wide range of courses like EE610, 613, among many others, where these things are taught extensively. Okay. So these are kind of, that's why you have these three compulsory courses. One is IC fabrication and the solid state, and there are circuit courses. Okay. Yeah. So there's the overall perspective. Any question? 683. Okay. So now the course content. Okay. Yeah. So essentially, this is around the device. For example, anyway, this is a bottom up approach. Okay. So at the bottom we have materials. Okay. So we need to know. So materials meaning we have crystal structure. You need to understand like how material. I mean, what is there? Okay. Crystal structure, stuff like that. Okay. Then you need to understand a little bit of quantum mechanics. The reason is that the device size is very small. Okay, in that dimension, quantum mechanical phenomena arise. So you need to have some idea of that. Okay, so essentially in this case, you will find that energy bands, completely quantum mechanical phenomena, these energy bands play a very critical role. Okay, so this is very important. So we need to understand. And once you are there, then only you are in a position to find the carrier numbers, meaning statistics, how many carriers are there. Okay, so now you know carriers inside material or crystal. Are you getting the link? Okay, so now you are at that position, you know how many carriers are there, but you need to push the carriers, right, so that it can move or it can flow. Okay, so that means now carrier transport. Okay, So here in the semiconductors, you will see something called carrier types, electron and holes, and how they are generated, okay, how they are recombined. These are the things also we'll be discussing. So all these together constitute the fundamentals or basics, okay. Still we are not into device. So these are the prerequisites, okay. So first 7-8 lectures, so we'll be discussing these very basic things, okay, these fundamental things. Okay, is it clear? Okay, once you understand fully these basics are or fundamentals, then only we can slowly move into devices. Okay, so here we are mostly focusing on semiconductor devices. The simplest junction device that you will come across will be PN junction diode. Okay, then we'll be talking about PN junction diode. We'll see how it works, its functionality, and how you model it. Okay, being an electrical engineer, you need to know the modeling. For example, this PN junction diode can behave like a resistor, okay, exhibiting which can exhibit rectification effects, capacitance. Okay, with resistor capacitor we can model things. Okay, these are the things we'll see together with electrostat, because electrostat and band diagram, these are very essential for this course. So once we have PN junction diode, so some junctions or devices with two materials. But of course, you understand when you have semiconductor devices, okay, essentially you need metallic contacts. So you have semiconductor devices, but you need to make contacts with metal, right? It could be aluminum, copper, something. Okay, so that's why this semiconductor metal interface is very important. Okay, so we'll see that essence semiconductor metal interface, how it behaves. So now when you have semiconductor and metal, so we can extend it a bit further and we can put oxide in between semiconductor and metal. Then we'll have metal oxide semiconductor. So essentially it becomes like a capacitor. Okay, so this is called MOS capacitor. These are the things we will study, and we'll study or we'll see ideal MOS capacitors, non-ideal MOS capacitors, and that is very, very important, because once you have MOS capacitor, the door is open. Okay, so you can integrate other stuff to that and you can actually make MOSFET. Okay, the key device for modern electronics. Okay, yeah, so MOSFETs are not only field effect transistors, there are also bipolar junction transistors. We'll have maybe 1 or 2 lectures on that. So this is so far the charge-based phenomena, but the semiconductors, you will see very soon that this band structure, band diagram important, and we can also have optical response. Okay, so optoelectronic devices we will also briefly cover in this course. For example, semiconductor, lasers, LEDs, okay, LEDs, photo detector, solar cell, okay. Now, those who are working or will be working in those areas will be helpful. Okay, so this is a broad overview of this course. So everything related to device, how it works. Okay. Any questions? Fine. Okay. So now books, references. I have already uploaded the first course handout. Okay, you must have seen it, and so you should check this resource section. Okay. But anyway, first course handout you can already see if you log in to this Hello ITK, right? Hello ITK profile. I have also uploaded all my lecture slides, I mean that I taught last year. Okay, there could be some typos here and there, but those will be helpful. So you'll know exactly what I'm gonna teach. Okay, but again after each class or module, again I'll post an updated one. But right now there is a zip file you should download and you will find all the lecture notes, okay, last year's. Fine. Okay. Okay, so now books. So there are several standard textbooks including Stedman Banerjee, Neiman, Robert Piret. Yeah, so these are very standard. Torrending's book is quite good for MOSFETs. Whenever we'll have MOSFETs, we'll use Torrending's book. Professor Alok Datta has written very nice comprehensive book. You can also refer to that. And whenever we have crystal structure or fundamental things, Kittle's book is pretty good because there are nice images there. Also, you can Google those images, but Kittle's book is pretty good for crystal structure. And for elementary quantum mechanics, Griffith's book is good, but it is quite vast. But whatever there in these basic semiconductors books in quantum mechanics, those should be fine. Okay, all clear for the textbooks. Anyway, we are trying to record this. If it is successful, we'll also upload. Okay, so but we are not sure. Okay. But if you want to have get access to other lectures, there are several. Okay, nowadays. So Professor Alam's from Purdue, you will find many lectures. So all are very good. Okay, if you miss any class, you can refer to those lectures. Okay, now yeah, yes, Alam, Purdue, yeah. But there are also other lectures from Karmal Clark from IIT Chennai. You'll find now many lectures. Okay, yeah. Okay. Now grading scheme. So probably you have been waiting for this. Okay, this is relative grading. Okay, so yeah, this is a relative grading as it says. So we'll have n number of quiz, typically 4 to 6. Okay, so it will have certain weightage, as you can see, mid-sem, end-sem, very trivial. So I don't give assignment problems because you will copy paste things from AIs. There's no point in doing it, but we will post tutorial problems. 7-8 set of tutorial problems will be posted. Those will help you in understanding, comprehending the syllabus and okay, this subject. Okay, if you solve that your own independently, then more, I mean, it's likely that you will get a good score. Okay. Instead of assignment problems, we'll have mini projects. Okay, 3 to 4 mini projects will be given. Those projects, I see this course is like theory course. Okay, so you may get bored. Okay, we have theory, but while working on these mini projects, you will get some feel like I will give you experimental data. So you need to fit, you need to analyze. Okay, essentially you need to work with those. Okay, to make things interesting. Sometimes you need to do some modeling. Okay. Yeah, so so we'll have assignments, okay? So we'll have mini projects. Is it clear? So we have, okay, let me just summarize. We'll have mini quizzes, or sorry, quizzes, a number of quizzes having quite a bit weightage, mid-sem, end-sem, and mini projects. Okay, so this is just a stat. Okay, from last year, student did exceptionally well. Okay, so average was around 7.7, which is phenomenal here. Okay, in EITK. Okay, so I'm trusting you guys. I really hope that you also do well. Okay, this time. Okay, is this clear? Course content structure, where to find materials, what to do. Okay, okay. Can we then go? Okay, move forward. Okay, so now our actual class is starting. Okay, beginning. So materials, because there's a bottom-up approach. Okay, so we need to study, understand materials, and then we'll build up our fundamentals and then devices. Okay, so if I say materials, okay, what are the things coming in your mind? Types of materials, right? So we can have metal. So metal meaning where you can push electricity. Okay, it can conduct electricity. Okay, and there can be another type, insulator, where it is kind of impossible to pass any current. Okay, for example, wood here and there. Okay, insulator. But these are not the only classification. So we can also have something in between, so known as semiconductors. Okay, so what is that differentiate, okay, or classifies? Okay, there are several factors. One is that yes, the magnitude of resistivity is fine. Okay, but we need to be more specific or scientific. Okay, for example, how resistivity changes as a function of temperature, whether you can tune resistivity or not. Okay, stuff like that. So we will delve into that. Okay, slowly, and eventually you'll see that all these things are connected. Okay, so eventually you'll see that this entire business is connected to band structure. Again, quantum mechanical phenomena. Soon we'll be discussing that. Okay, yeah. But anyway, you understand that metal, insulator, and in between we have something semiconductor. But it seems that this semiconductor is the most interesting thing. This is the entire periodic structure. and you can see that there are several metals and some insulators, and right there we have two key elements, okay, for semiconductors, silicon and germanium. There are some more, okay. These are the two important ones, silicon and germanium, okay. Okay, so I mentioned that metals have high conductivity, meaning low resistivity. Also, there are also other classifications. This beyond this scope. Okay, you need to go, I mean, at an advanced courses for that. But anyway, uh, yeah. So for metal, we have it can conduct more, right? It has a high conductivity. Okay, so do you need high conductivity or low conductivity for your devices? Higher conductivity is better or worse?
Depends.
Depends. Why? Can you explain?
Majority electronics is our semiconductor.
No, that is there. No, that is there. But I'm asking other way around. In general, having higher conductivity is better, good or not?
Electricity, transport electricity, those are surrounded with insulated wire to prevent getting shock. And but the inner conducting medium is made of metal, so both are needed in some ways. Insulator is
Okay.
usually for shielding and conductor for conducting.
Okay, but if you look, there are also superconductors showing nearly zero resistivity. Okay, people really try to have room temperature superconductivity, but could not do it. Still, research is going on. But yes, thanks for your answer. Any other comments?
It depends on the application. Like if you want heating application, then we need a higher resistance. So we need lower conductivity. And if we want the other way around, like
Okay, so let's go one step back. Okay, we have electronic devices. Okay, let's keep optical devices. Okay, Aaron. So for electrical devices or electronic devices, what we want IV, right? I versus B or CV, right? These are the fundamental things. So we are we connecting devices to voltage source and getting the current response. You want more current or less current? More current. Then you will want higher conductivity or lower conductivity. Then why semiconductor? Yes, that is the key. Okay, so only not about the conductivity, you want to control them. Okay, yeah, and it turns out to be that if it is semiconductor, we have better controlability. We'll learn. Okay, so we'll see that we'll have better control. Okay, and that's why semiconductor is important. Essentially, the transistor is like switch. I mean, there is a flow of current or carriers between source to drain, and you want to control with a gate, and that control is possible with semiconductors. Okay, that's why it is important, and we'll see how to control the carriers. Okay, carrier numbers, everything. Very good. Is it clear? So now you are convinced, right, that semiconductor is important. I mean, you need that control. Everyone wants to control, right? You want to control something in your life, right? Yeah. Okay. Okay. So this is the focus, silicon and germanium. So these are semiconductors elements, elemental semiconductor, right? You understand, right? What it means, element. Okay. Yeah, but these are not the only options. If you see this, it is group 4. It has a valence say 4. Okay, silicon and germanium, and it is in the sweet spot. Okay. So now, if you, there are other ways. Okay. For example, you can take this group 3 elements and group 5. Again, average is 4, and combining them, you can also have semiconductors. For example, gallium arsenide. Okay, so here gallium group 3. So these 4, these 3, arsenide. Okay, 5 gallium arsenide, gallium phosphide. Okay, gallium nitride. You can also do with others, indium phosphide. Okay, indium arsenide. Okay, fine. So these are called 3,5 materials. 3,5 semiconductor materials. Okay, so again average is 4. you'll understand why that's important soon. Okay. Now we can also do 2,6. For example, zinc oxide. Zinc is probably not shown here. Maybe. Acha, it cannot go back.
We can go back.
Anyway, so, anyway, leave it. So do you see zinc? Here. Okay. Zinc oxide. Okay. See cadmium telluride. These are more sophisticated and fancy 2,4 semiconductors. Okay, they also exist. So these are again compound semiconductors. So you understand what is element and you understand what is compound. Okay, and there is something else called alloy. There is a difference between compound and alloy. Alloy is just mixing. Okay, so when we have alloy silicon and germanium, okay, it has properties of both silicon and germanium. That's alloy. But compound gallium arsenide will exhibit completely different property as compared to gallium and arsenic. These are very basics. Okay, element, compound, and alloys. Okay, so we can have alloys, semiconductor alloys. Okay, with silicon, germanium, and also you can dope with something and make all these fascinating. Okay, what are the applications? Generally, so you will find a wide range of applications in photonics. Okay, because later on you see, so whatever I'm having, I know most of you already know, but we'll again discuss. So this band gap tuning, okay, all these things will play a very critical role. Okay, yeah, and you want to tune the band gap, and with this allowing or having this compound in this compound materials, we can have a desired or optimum band gap and also band location. Okay. Okay. Now, so the summary is we have elemental semiconductors, compound semiconductors, alloys. Fine. Clear? Okay. So now, yeah, this is how it looks like. Okay. Maybe Raj, you can help. So these are here. You should wear gloves. So maybe from this you can try to see, or maybe you can use these cottons. Okay. So these are silicon wafers. Okay. 3-inch most likely. 3-inch silicon wafers. Okay. So this is how big wafer looks like. One can cut with a slice and get. So yeah, again the IC fabrication course, this will be covered, like how you process it. Okay. Yeah. Please take a look at it, how silicon wafer looks like. And also we have devices. I mentioned there are devices. Okay. So in this course, mostly we'll be working on the fundamentals, but let's take a look at it. In other course, you'll see how devices are fabricated. Generally, in our experiment, we usually fabricate these in our clean room facilities, and we characterize. Okay, yeah. So anyway, you can take a look at it how it just to have a feeling. Okay. Okay. So these are silicon wafers, and you will fabricate devices, right? Okay. Now, so we have the material. So this is EM image, okay, of a stack, okay, which we have grown this from one of our works. Okay, so this is image. So this is a TM image. So there you can see 3 different things. First, there is in this material, okay, so you can see a nice orientation, or atoms are periodically located, nicely organized. Do you understand? So here this is a schematics. Okay, we call it single crystal or crystalline material, meaning all atoms are nicely oriented in proper phase. Okay, yeah. So there is also another variation. So here, I don't know if you can see this. So there are orientation patterns in some of the domains. For example, so here you can see one of the domains. It's frozen. Maybe you can see here say some domain here, okay? But this looks different here. Okay, so here if you carefully look, this looks like this kind of stripes. But here it is like this. Okay, so there are orders, but these orders are there locally. It is not present entirely or globally. Is it clear? So we have local ordering. So we call it polycrystalline. So it is not crystalline, it is crystalline in some domains. But as a whole, it is not crystalline. So we call it polycrystalline. And of course, the third type is very obvious. There is no ordering. Okay? So we call it amorphous. These are three different types: crystalline or single crystal, polycrystal, and amorphous. Okay? Generally, the materials we have, silicon wafers, these are single crystal. Okay? These are single crystal. Okay? So, what we need to learn and understand in this course? Crystal structure. Is it fine? Okay. Okay, so this is a definition. So periodic arrangement of points called lattice. Okay, all are lattice points. So here in this picture you can see two-dimensional lattice. Crystal forming in 2D, because this is easy to visualize. 3D is a bit complicated, 2D is much easier. So do you agree that this is periodically arranged? Do you agree or not? Agree? So if you agree that it is periodic, then we must have periodicity. What is that periodicity? So that means we can define cell or block, whatever you want to say, and we can repeat that, okay? And we can construct the entire surface without leaving void. Okay, maybe this is one of the, so this is called unit cell. So this is the cell. So I can copy this everywhere and recreate this crystal structure. This is 2D. Do you agree? And there will not be any gap. I'll show you where we can have gap later on. Do you agree? So this rhombus kind of thing we can copy and create this entire surface. Okay. But instead of taking this, I can take this bigger one, right? Still we can do the same thing. So this is called unit cell. The definition is that this unit cell can reproduce a whole structure by periodic repetition. There is one part missing, without leaving any void. Okay, same thing here. So note that I can have it like this, and imagine we copy it here. Okay, and we can reconstruct this entire surface. That means this choice is not unique. Is it clear? We can have, different unit cells, which is fine. Its choice is not unique. Is it clear? Okay. Okay. So now you can see some of the cells bigger. Of course, some of the cells smaller. Right? So we can have, or we must have, the smallest one. Okay. So we'll have the smallest cell, right? And we call it primitive cell. So unit cell, that means all primitive cells are unit cell, but all unit cells are not primitive cell. So this is the smallest one. Do you agree? This is the smallest one. You can try and check. Okay, you can't make it smaller than that. You can make it bigger, but you can't make it smaller than that one. Okay, so this is called primitive cell. Okay, again, the choice of primitive cell is not unique, because this is one primitive cell. This is also another primitive cell, right? Do you agree? I just rotated it. I can copy it here and recreate this entire surface, and I can also copy here. Do you agree or not? Do you understand? That means this choice is not unique. Okay? So you are getting what primitive cell is? Okay, now what we need to define? So now we have a cell. So for sake of 2D is easy. That's why we have taken this example 2D. So now we have a cell. If it is 3D, we could have a volume. Okay. So now, okay, if it is, so here this is a surface. Okay. How many vectors you need? Okay, to construct this surface or to have this unit cell or primitive cell, how many vectors you need? two vectors, right? Because if I have vector A and vector B, A cross B gives you area. So A cross B dot C gives you volume. So you need two vectors. So here we have these primitive cells or unit cells, and we can have associated vectors, okay, by which we can have this well-defined area or volume. Those vectors are called basis vectors. Okay, just one example. This could be one of the basis vectors. Again, the choice is not unique. I can also have basis vectors here. Because if my choice for unit cell or primitive cell is not unique, then choice of basis vectors will also not be unique, right? Okay, but there are some crucial things. For example, these basis vectors will always be linearly independent. So if it is 2D plane, we can have two vectors which are linearly independent. Those two vectors can be different. Okay, so now, yeah, so that's point number one. Point number two, if you add two basis vectors, then you get another basis vector. Okay, I'll give you one example. Let's take, so do you agree this is a basis vector? Because this could be the unit cell, this rhombus. Are you with me? Are you able to follow? So now if I add these two basis vectors, so I will get this kind of diagonal basis vector, sorry, diagonal vector. Okay, then that's exactly what I mean. So this diagonal vector, and if I take one of them, either this or that, so this diagonal vector will also be another basis vector. So now I can have a surface based on this one and this one. Okay, so this is one of the unit cells. Okay, you can imagine that you can copy it here and there. Okay, is it fine? You are able to get this? Yeah, so that means addition of basis vectors will again give you set of basis vectors. And the position is not unique. The reason is that so there is no starting point because it's infinite. So always I can relocate my origin. Okay. So anyway, here the basis vector doesn't mean that it will be unique. Okay. So again, we can define primitive vector, meaning so the vectors required for the primitive cell. For example, this is one of the primitive cells. Okay. So this is known as primitive vectors. Okay. Meaning the basis vectors for the primitive cell. Okay, is it clear? Again, I can add these two primitive vectors. If I add these two primitive vectors, will you get a primitive vector or non-primitive vector? You'll get another primitive vector. So I can have, okay, so I think you are able to follow this, right? Okay. Yeah. So in general, we call this lattice, okay, but technically it's known as Bravais lattice. Okay, we call, so technically or mathematically, we call it Bravais lattice. And you may think there can be infinite number of possibilities, right? But that's not the case. Because this is deeply connected or related to mathematics and group theory. We will not get into that. But I'm just for your information. This is deeply connected or related to mathematics. So there are only some groups possible. In 3D, there are 14 such cases, and 2D, there are 5. We'll start, of course, with 2D because that's easy to visualize. Okay? Okay. So now this page is gone. Is it clear? Yeah.
So in that cell that you made in pink, in the pink color.
Correct.
So you have taken two basis vector and
right.
the resultant gave another basis vector.
Right.
So the cell is formed using the resultant basis vector.
Plus another. You need two.
So what if you take
you can.
vertical instead of the horizontal?
Yes, you can take it. Then it will be like this here. Okay, let me just try to. Okay, somehow it's not responding time to time. I was thinking, yeah. Okay, are you able to follow this? So this will be one. and this is 1, right? Then you have this cell. Looks weird, but it works. You can copy it again and again here, and you can get this entire surface constructed without leaving any void. Okay? Clear? Any other questions? Any other questions? All good? Yeah.
The vectors you just choose, like the bottom one and the top one, it will give a certain vector in the diagonal, like
Yes, here, for this case.
like a full diagonal.
Yes.
So it will also be a big basis vector.
Yes, that's the thing. If I add, okay, two basis vectors, we get another basis vector. If you add two primitive vectors, you get another primitive vector. Okay, just let me show you how would another primitive vector look like. Okay, if I add these two guys, this vector, so I will get one here. So then my primitive cell could look like this. Okay, and you can copy, and you can mathematically check that this cell and this cell will have same area. You can verify it. Okay. Yeah.
Which two set?
Yeah, he said this blue one and this shaded one. Okay. Yeah. Any other questions? Fine. Okay. So now, question for you guys. This is very famous crystal structure of graphene. Okay. Graphene is very important and exciting material. Honeycomb structure. You have seen honeybees. Okay. Like, imagine we have it in 2D. Okay. Graphene. So, yeah, first of all, is it a Bravais lattice, or do you think we have periodic structure here? Is it periodic? Then what is the periodicity? If I'm asking what is the periodicity, I'm asking what is the unit cell. Sorry? Hexagon. If it is hexagon, yeah, so this I'm okay. Yeah, let me just try to draw this. Probably, okay, so one by one, let me just, it's okay, this issue with my.
If it is lagging, then we can pause and start it.
It's
from
okay,
correct
it's okay.
slide.
So you are saying this hexagon, right? Okay.
Sir, it is like the three hexagons connected, like the top, then middle, and one bottom connected together forms a like the top layer. will
Here.
be one, then that diagonally that middle one, then
I'm not sure what you are saying. Are you saying maybe can you come to board and draw? That would be easy. Okay.
like top, then this will
So he is saying that consider three of them. Yeah, but anyway, whatever. Okay, let me just take one small one. Okay, then you will understand the issue. So here, so someone said this is a unit cell, right? Okay, that means if I copy paste it, and copy pasting means this, it doesn't get there. By same way, whatever you are saying will have something like that. This is like mosaic things you might have seen in some houses. Okay, because you have this void. So this is not unit cell because it will live like it will be like that. Okay, why? I just tell you. I just give you one more hint. Look at, okay, focus on this guy. What it sees, one here, because you need to also think in terms of vectors. Okay, if so, this side has three arrows. Okay, now if I focus on this side, then we have arrows inward. Is it clear? I mean, okay. If you assume this is consistent, then this guy feels like arrow coming in. That means this point and this point, they are not equivalent. There is a pattern, perhaps there is something, but this is not so-called Reveille lattice. Are you getting it or not? So these 2 points are not, so here, this point and this point, or this point and this point, they are not equivalent. They see different environment. Okay? Okay, let me give you, okay, so this 2D, so it's a bit complicated probably. If it is complicated, let's simplify it. Let's have a similar thing for 1D. Then you will understand how to solve for it. Okay? So, what is your opinion? Is it periodic? Periodic. What is the periodicity? Okay, now it is a bit easier, right? But again, yeah, okay, now focus on this guy and this guy. They are not equivalent, right? So for this, so left side is close, right is far away. For this, left is far away, right is close. But it seems like periodic, right? I understand the emotion. But mathematically, we have to justify. How about combining them together? So instead of these, I just group them. So this is one group. So this one group has 2 lattice points. This one group has 2 lattice points. Now this group is periodic, and each group has 2 sides. Do you agree or not? This group is periodic, but each group has 2 sides. Okay, make sense? Then it is fine. Yeah. No, so this is a group. So this is one side, another side. Okay. This is how you can shuffle things around and see whether it makes sense or not. Same thing we can also do with this Reveille lattice. How? Let's do one thing. So these 2 sides are different, like here and here. Let's combine these guys. Let's assume this is 1, this is 2, this is 3, this is 4, this is 5. And let me just have points here. Okay? This. Is it okay? That exactly I meant. These 2 together, this star. And this star having 2 sides. So this is this star having 2 sides. Now this process repeats. Even for the time being, if you forget these 2 sides, now if you focus on these lattice points, then this is exactly the same thing I discussed earlier, right? So then this is the one, this shaded one is our unit. Actually, this is primitive here, and these are our basis vectors. Now it becomes Reveille lattice, one type of Reveille lattice. Okay? So when we have lattice, okay, so we need to do more stuff, okay? Using them, we need to find band structure, stuff like that. That's a defined question. So we are understanding lattice because we'll exploit this periodicity, okay? And we'll use this to find band structures later on. Later I will tell, or there will be one mini project there you'll exercise that this kind of things, okay? If we have several on-site, okay, if you have on-site atoms as shown here, how you handle, okay? But overall, is it clear? This is very important. So whatever looks, I mean, barely periodic might not be Reveille lattice. That's the essence. Okay? Are you able to follow this? Okay. Okay, now, so in 2D, it is easy to visualize, okay? So in 2D, there are 5 types of Reveille lattice, and in 3D, there are 14. Okay, these 5 types are not that difficult to understand or to visualize. So one type is this. This is kind of square. You understand, right? For a square, all lengths A and B same, and the angle between them 90 degree. Okay, so the square lattice we can have square, fine. Okay, if it is square, then this is called C4 or R90, 90 degree, I mean fourfold rotational symmetry or 90-degree rotational symmetry. What do you mean by that? If you rotate the system by 90 degree, this is a plane, here there's a square lattice. If I rotate it 90 degree, we'll eventually get the same thing. Another example is rectangle. Okay, rectangular 2D Bravais lattice. It has twofold rotational symmetry or 180 degree. What do you mean twofold? If I rotate it 90 degree, it doesn't go there. Here, I try to show. This is okay. If I rotate it, how will it look? It will just be vertical. Do you agree? So these two are not same. But imagine if this was a square lattice, then it would be same, right? That's why for square, so this is a 90-degree rotation, meaning if I have a square lattice, if I rotate it 90 degree, we eventually get the same thing. So this is a 90-degree rotational symmetry, or we call C4. 4 meaning 360 by 90, so C4. So here it is C2 because twofold, 360 by 2, okay, or 180-degree rotational symmetry. Is it okay? So now here you understand rotational symmetries. There are different symmetries present. We'll not understand, I mean, discuss everything, but little bit, okay? Okay, what are other options? One of them we have discussed. Anyway, so here to here, again, if I rotate, then it goes back there, okay? Is it clear? Okay? Okay, now this is a special case. If A and B are same, and if angle is 60 degree here, or maybe 120 degree from that side, then we call it six-fold rotational symmetry. These are the hexagonal system, 2D hexagonal system. So this is special because this is a unique way that, so this hexagon, right? So I hope you are able to follow that. If I rotate this entire thing by 60 degree, I will eventually get the same structure. Okay, so it has six-fold symmetry or R60. Okay. What other options we have? The square is easy. So anyway, here if you see, this is kind of rhombus which we looked at before, but angle is 60. But we can have another variant like this kind of rhombus sort of thing, but angle is not 60, neither 90. Something oblique. That is, if this is the case, then by any rotation you cannot get back. It has to be 360-degree rotation. So it's called an R0. Okay. So because if you rotate it, you can. So this is if there are 90 degrees. So here angle between two axes. If they're 90, then it is for square. It is twofold. Sorry, fourfold, meaning 90-degree rotational. If it is rectangle, it is twofold, 180. And if it was hexagonal, then it is sixfold. But if it is some arbitrary angle, then there is no fold essentially. No fold meaning this is R0. Okay? Then only you can have translation. But you agree, right, that this is a unit cell. So the angle can be oblique. Okay? These are different groups. Okay? Yeah. So one last thing. So is it okay? So you are understanding different types. So these are classified essentially by rotational symmetry. Okay, one last. So whenever you find something and if you don't know what to do, you put another crystal in between, sorry, another lattice in between and see if a new structure emerges. For example, if you keep adding one here, do you get a new structure? You will not get a new structure. So if you have it, probably the unit cell would look like that. Yeah. Sorry, so the unit cell, sorry, not this, will look like that. Yes, someone asked some question. Any question? What I mean, so here, if I take this and put a lattice, it still is a square lattice. You are not changing it. Same thing for others. But if you do this here, essentially you get a new type. For example, let me just show here. Okay. So in rectangular lattice, if I put a center, sorry, in a rectangular Bravais lattice, if I have a center lattice point, then we get a new uh, crystal structure in 2D. So this is called centered rectangle. So it also has C2. Okay, and also here A and B, they are not same. So try to understand the difference. So this is, I mean, different from this, right? But here they are same. That's why this structure is different from this. Okay, and essentially this is a new type of, or the fifth class of Bravais lattice in 2D. Let me just summarize. So here in 2D Bravais lattice, so we can visualize, or you can see there are 5 types. Okay, typically determined by the rotational symmetry. So why only 60 degree, 90 degree or stuff like that? Because in mathematics it is found that in this kind of crystals, so without leaving void, okay, these are the only possible rotations allowed. So if you take other rotations, definitely there will be void. Okay, that derivation we don't have to do. That's why this key rotational symmetries are arising, and based on that, and when you try to find out a new type of crystal, you see what is that rotational symmetry. Okay, yeah, yeah.
What does CAR stands for? Like in C for an R.
C, R for rotation. This R for rotation. So just a second, let me, yeah. This R for rotation. So R 180 meaning 180 degree rotation. Okay, and C for I just mentioned that word. I twofold. It determines by the fold. Twofold, threefold. Meaning, let's just go back again. C4 is the fourfold symmetry. Okay, fourfold symmetry means 360 by 4 is 90. So C4 by default means 90 degree. C is just a, I mean, representation. Okay, it is 4 versus 90. 4 means fourfold, twofold, sixfold, like that. Okay. Happy, or other questions, concerns?
Between the square, it will not get a new structure, but I can see similar hexagon forming there also.
So you can see different patterns. Yeah, so similar hexagon, right? If it is hexagon, it is already existing. It belongs there. I could be wrong here showing the primitive cell or unit cell, that exactly you have to check. If I'm having it, if you think, yeah, if you feel like we are having hexagon, that means this is not a new structure, already it is defined. But for rectangle, it is a different thing. That's the key difference. Okay, and if it is oblique, if you put something, it will be oblique again. Okay, it is not giving something new variant. Okay, yeah.
That phi angle is between the both the sides.
Here, the what I say, vectors, basis vectors.
So in that center rectangular, the phi is given 180.
Oh, so no, actually this is, yeah, I'm sorry, this is not that, this is the rotational symmetry. It is 180, yes, very good point, thanks. It is, yes, it is 180. The reason is, if you rotate these by 180, then only you, yeah, you can reproduce it. So this phi is not angle between these, this is a rotational angle. The amount you need to rotate, okay?
What will be the angle specification there?
So, yeah, you need here multiple vectors, or you can define unit vectors accordingly. So maybe for this case, this also seems okay. But there is a difference here and there because this is 60 degree, but this is not necessary. Okay, so I'm imagining if I'm copying this guy, I can repeat entire stack, copying here, this direction, this direction. Okay, anyway, I'll check. Okay, yeah,
If we introduce obliques
right.
at a point,
Huh.
how it will be?
It will be again oblique. So oblique meaning there is no rotational symmetry. So if I have some points here everywhere, it will also not follow any rotational symmetry. Meaning you need to rotate it by 360. That means this is a new type. Types are defined by rotational symmetry. So there is no rotational symmetry in oblique. If you introduce a new atom, there will not be.
And in all of these cases, we are interested in the
So if you have points here, so new structure will be one of these. That's the point. So whatever we have, it will be one of them. Yes. So it will not give. So if I take this 1, 2, 3, 4, 5, if you put points here in between, it will belong one of them. Okay, I think he mentioned that if it is square, it becomes hexagonal. Anyway, I have to check and visualize, but that's what he said.
It means in 2D we have 5.
Five.
Because we have 5 types of rotations. So same.
Rotations are kind of same. No, rotations are kind of same for 2D and 3D. So there is a 5 times that is possible. It is, I mean, we check with the rotations, okay, but in 3D you'll see more. It is not because of 5 types of rotation. So 90, 60, 360, see, there are not 5 types, right? We have 60 degree rotation, 90 degree rotation, 180, and yeah, one fold, 360. 4 types of rotation. Yeah. So these 4 types of rotation giving 5 different groups.
Different types, like one the center square and one.
Yeah, but center square, eventually I have to check and visualize either becomes center square or it is becoming like hexagonal. Hexagonal, if it becomes like center square, square, it is already square, it is a new thing. If it becomes hexagonal, it is already included. That's the point. Okay, so yeah, you just need to put them and see exactly what it forms.
Then here also you can make rectangle. That's
Here.
rectangular.
No, here, no, it is not. So there's a, yeah. So there's a difference. So here, this oblique angle, here, whatever angle we have, this angle is different. So here, this angle is 60 degree. And this angle, just 1 second, this angle is different, but that different angle finally making the entire thing twofold. Okay, that's why it is fundamentally different and new type. Yes.
Sir, when you put one dot in between of the 4 in the first,
Here, yes.
it looks like a parallelogram.
Yeah, it will be parallelogram. Yes. So eventually you have to see whatever structure you have. Okay, that's not that easy for me, I mean, to visualize, but this will fall one of these categories. That's what I mean. Okay, you just print it and put those lattice and see if it resembles these, that. That's a good exercise. You can actually do it. Yeah. These are 60, correct. Sorry, where? These are 60. Yeah. Oh, here. Okay, this is a mistake. Okay, this should be 60. So 60 will definitely be 120 because you can rotate one more time, but 120 might not be 60. Yeah. I mean, yeah. Thanks.
Sir, phi is the angle of rotation by which we need to rotate to get it back.
Exactly.
So for the oblique wire, should it be like
360.
360 only?
Yes. That's why R1. 360. Full. 360 by 360, 1. So here for square 360 by 90, so we said C4. Okay, 360 by 180, we call it C2. These are the only possible options, C2, C4, C6. Yeah, C3 is kind of here, C6 is by default C3. Okay.
So should we have 30
In principle, you can say, but if it is 30 degree, so mathematically you cannot have crystal structure which will reproduce the entire structure without leaving void. Someone can ask if it is a football. Okay, IS type of question. So hexagons are there. Why you need pentagons? Because in 3D things change. Okay, so you need that.
So main concern is there should not be any void.
Yes, yes. So these are the possible ways that mathematicians figured out. So yeah, you can't have any other combinations. Okay? Okay. So now let's get into this 3D. Sometimes it's not working or maybe slow.
So, sir, one given structure can have different types of lattices based on the based on the unit cell things. It can have different types of lattices, like any one single crystal structure. It can have more than one type of lattices.
Okay. No. So once it is determined, okay, then it is a given lattice cell. Okay. So unit cells are not unique. You can define many different ways. Okay, sometimes we define it as per our convenience, which we can visualize. Okay, but the key thing is a primitive, the smallest unit cell. Again, that is not unique. You can define, at your convenience. Okay. Somehow this is not working, but anyway, these are 3D Bravai lattice. So previously it was 2, now 2D to 3D. Things are difficult, but overall you'll understand. So previously we had square. Now in 3D it will be cube, one type. I mentioned always put some atoms in between. In square you have put that, but I'm not able to. Oh, now it's working. Okay. So in square, we have put that, right? One atom. So here you can put at the center. We call it body center. I'm not trying to justify why this is a new type, because for 3D, it is 2D. It was already complicated. 3D, it is quite. But these are the ways you can think. Okay. Now, instead of having that in the body, I can have at the faces. Then we call it FCC. These are the 3 different types. So previously we have seen rectangle. Okay, now we can have it in 3D version. We call it tetragonal. So we have seen hexagonal in 2D. We can have 3D version of that. Okay, and now these are called orthonomic. Anyway, you spend more time and you will understand that you can put again at the center, at the face, okay, and top and bottom. Okay, stuff like that. And this is like oblique, neither 0 degree nor 60 degree. Okay, these are different variations. Okay, we don't need to go everything in detail, but you can try to visualize. Okay, for your understanding, you will find many photos, videos. Okay, feel free to check those things out. But overall, is it okay? Like in 5D, we had 5, and at least some of them you can easily visualize, right? In 3D, we'll have 14 different types. Is it okay? Okay. Okay, so now, so these are the overall broad idea. Okay, so see, there are 14 different types of crystals. We'll not discuss all of them, of course, right? But we need to understand some of them, the most critical ones. Okay, in this course, at least 3, 4. Okay, so this is the most simplest one. Do you agree? In 3D, this is called simple cubic structure. So we have 4 lattice points here, and this structure is repeated itself. Is it okay? Okay, now questions for you. There's something called coordination number. Coordination number is, so imagine this is the chain of that. I have only shown 1 cube. Imagine there are 100 cubes, okay? You have seen this Rubik cube. Imagine that, okay? And now focus on one of the points. Okay, now tell me this, point is connected to how many neighbors? 4, 6, any? Okay, I can say 1 here. You agree? 2 here, 3 here. This is far. 3. Here we'll also have some 4 and yes. Okay, better visualization. Here you have to visualize. Okay. So this is this block. This is center of that. Okay, this side, this side, this side, this side. One top, one below. So this here, here, up, down, meaning x, x, plus x minus x, plus y minus y, plus z minus z. Okay. So this is called coordination number of 6. Coordinated. Okay. Fine. Okay. Let's see what's coming next. Yeah. So now, so imagine I'm filling. So here at these lattice points, I'm filling with sphere, solid spheres. How many spheres I can have? 4. Like that. Okay. Now some part of the spheres are inside and some are outside. Effectively, how many spheres are inside? How do you know? Yeah. So what is this volume? So I have this entire thing. I slice to 2. Okay. Then I slice again, slice again. So this volume is 1 by 8. 1 by 8. We have 8 corners. So 1 by 8. Yeah. So we have effectively 1. Okay. Yeah, a little bit more mathematics, because sometimes if it is not that easy, this is how you find the volume of a sphere. R square sine theta d theta. So here theta runs from 0 to 90, right? Phi runs for 0 to, okay. Yeah, so there's 1 by 8 and we have 8, so essentially 1. Okay. So now, so we need to know like the fraction of volume occupied, called packing fraction. So what is the, so okay, that is what is the volume of this cube? If this is A, the unit, so this one is A cube. Okay, and what is the volume occupied by these spheres? You need to figure it, right? 4 by 3 pi r cube, right? So we need to find relation between R and A. What is the relation between R? So this is the one, right? 4 by 3 pi r cube, right? So what is the relation between R and A? Very simple, right? The volume of sphere is the following. This is a packing fraction. So how much the sphere is occupying? Huh? Yeah, so whatever. Okay. Something like 50 or whatever %. So what does it tell you? So it somehow gives you an impression how much a unit cell is filled. Because when we have our real crystals, well, we'll have periodic arrangements, right? Points. There are voids. So sometimes due to defects, okay, some other things can sit in those void places. Okay, if you have more void, chance is higher. Okay, that's why this packing fraction is important. Okay, this was really simple, right? Okay, so our next thing is BCC, body centered cube. So this is simple cubic structure and we have one lattice point at the center. Is it okay? This is called BCC. Okay, now tell me what is the coordination number? How do you know? Which one you consider, this point or that point? This point, right? So here I'm filling this with solid spheres and this is connected to all neighboring spheres, right? Coordination number 8. Okay. Then what's next? So how many spheres do we have effectively inside this box? How do you know? Yes, so one coming from this corners, right, as we had earlier, and one sphere already you can see inside. So effectively 2, right? Then can you find the packing fraction? So packing fraction, did I do it? Yeah. So 4 by 3 pi r cube. So you need to find the relation between R and A. So previously it was very simple. 2R, A was 2R, A equals to 2R. Now, so you need to consider.
4R equals to
Yeah, I mean, so we need to consider this diagonal, right? So here we have one R, right? Here we have another R, and here we have 2R. So 4R, that's what you said, right? 4R equals to something like this, right? A square plus A square plus A square, right? Is that? Huh? And if I put all the things back, then I didn't have the. Anyway, you can calculate it. Okay, fine. Now another type, which is FCC, face-centered cubic cube. Okay, so again we have the same cube. Previously we had it in the center, at the center. Now it is at the faces. Okay, so what is the coordination number? Anyway, you can check. Most likely that's true. Okay, and what would be the packing fraction? Now you know how to calculate. So you need to find how many spheres are effectively there. You can calculate, okay, for your homework. Okay, very simple things. AFCC. Okay. So I would encourage you to search. There are different materials, for example, sodium chloride, which one forms what type of crystal structures. Okay, these are there, but never forget our focus should be on silicon. We need to know what happens with the silicon. Silicon, acha, before that, okay, there are two variants. So in this space is there for you, so that you can calculate it and, okay, fill it out. So this is called diamond lattice. Diamond lattice is two FCC lattice. So these are FCC lattice, okay? Okay, but shifted by 1/4, 1/4, 1/4. Did you understand what I said, or too complicated? Imagine one FCC lattice. Imagine another FCC lattice. Put it inside. Okay, and shift the other one by 1/4, 1/4, 1/4 with respect to the origin. So say this is the origin. So this is the simple FCC I had here, and now another FCC I shifted by 1/4, 1/4, 1/4. And what had happened that some of the points, these four greens, are falling inside this cube. Some are others. So these are a bit difficult to visualize. The best thing is that you figure out. Okay, you will find a lot of videos, animations of diamond lattice, and also in Charles Kittle's book you will find. He did try to do best. Okay, but anyway, now there are a lot of photos and videos on internet you will find. Okay, diamond lattice. So again, this is very important. You need to know the packing density, and this is the most critical one. And of course, this is not that easy. You need to, okay, do it carefully. Yeah. So another one is HCP, hexagonal close packed. So we have seen the same thing for 2D. So now this is for the 3D. Okay, these are how hexagon. This is how this crystal structure looks like. Have you seen eggs? This, and if this is layer 1 and layer 2, between the gap you put other eggs, right? It's something like that. Okay, we have balls forming this type of hexagon, 6, and center we have, and in the next layer it is, balls are there in the slots. Okay, yeah, again questions like what will be the packing density, stuff like that. So here the overall, so you got the overall idea how to do it. Okay, you need to do the same thing for this structure. So your homework problems, tutorial problems will be posted. So, but anyway, okay. Okay, these are more or less. So in the next lecture, we'll see more. For example, this one on the, anyway, I'm not discussing it. I'm just giving you a brief idea what is coming next. So what are the primitive cells? Okay, so the kind of, say this was the BCC, right? But this was on the primitive. Okay, how to find primitive cells? So this is the primitive cell of BCC. You will not believe. Okay, but there are ways for finding out primitive cells. So weakness size we will discuss. and important things coming. Okay, yeah. And when we have planes, crystal structure will have planes. We need to define planes. Okay, called Miller indices. We will discuss different type of planes. Okay, and yeah, so here periodic arrangement of atoms, right? For electrical engineers, when you have seen periodicity, you become excited because things are related to Fourier series or Fourier transform. Yes, for lattice, same thing is applied. So if you do the Fourier transform, it goes into reciprocal space because lot of times a different opinion, a viewpoint is important. Okay, you should have both the sides. Okay, when you are following news channels, different news channels for different viewpoints. Okay, otherwise you will be biased. Okay, so real space, reciprocal space, all you need to analyze. Okay, so with this, and when we have this finally experimental part.